Hello and welcome to today's lesson on resolving vectors, which is part of the forces topic in GCSE Separate Science Physics. So in today's lesson we're going to look at how you can resolve vectors into different components. So if you've been successful and learned in today's lesson, you should be able to define what a vector quantity is and how we can resolve them, describe how we can represent vectors, and explain why we resolve vectors in the first place, which links into the following part of the GCSE Separate Science Physics specification, resultant forces. Now just to clarify, if we have two vectors which are not at 90 degrees to each other, you can still add them via scale diagrams, because to find the resultant vector you must use something called the parallelogram of forces. So to carry out a parallelogram of forces, what you need to do is firstly draw in the same length vector as vector 1 with the same angle on the opposite side of vector 2 as shown in the following diagram. Then you draw in the same length vector as vector 2 with the same angle on the opposite side of vector 1. Now what you've drawn here is a parallelogram of forces, because you'll notice now we've drawn a parallelogram. Now then, to find the resultant vector, you draw your vector from the start of the original vectors to where the new lines meet up. So to find then the size of the resultant vector, you measure the vector with a ruler and convert it to a value with a scale. Then to find the direction of the resultant vector, you measure the angle with a protractor. But whilst you can add vectors, it's also possible to break a diagonal vector into its perpendicular components, and this makes it easier to describe the motion of the object and do any relevant calculations. So if we consider a resultant vector, well, this single force can always be resolved into two component forces at right angles to each other. Now to resolve means to split, so the single force can be resolved into horizontal and vertical components, as shown in the following diagram. Now here, the resultant vector is denoted as f, and the angle phi is from the vertical and angle theta is from the horizontal. Now we can now consider this resultant vector in terms of its vertical component, fy, and its horizontal component, fx. Now it's important to note that f squared is equal to fy squared plus fx squared. Now we can express these components with the following equation. Now just note, I've swapped the position of the vertical axis to allow you to see the concept that this is just a right angled triangle like we drew previously. Now again, in this process you must use the angle produced by the vectors and not the direction reference, so you've always got to look at the angle used carefully. So we can now describe our horizontal component as f cos theta and our vertical component as f sine theta. Now these two values come from trigonometry, because we know that sine theta is opposite over hypotenuse. So in this example, the opposite of theta is fy, and the hypotenuse in the right angle triangle is f. So sine theta is fy over f. So therefore fy is equal to f sine theta. So this comes from the trigonometry ratios. And also we know that cos theta is adjacent over hypotenuse. And so the adjacent to the angle of theta is fx. Our hypotenuse is fy. So cos theta is fx over f. So therefore fx is equal to f cos theta, which once again comes from the trigonometry ratios. Now these equations can then be used to calculate horizontal and vertical components. So let's for example take a resultant vector with 10 newtons at an angle of 40 degrees. So we pop this into the equation where fy is f sine theta, so it's 10 sine 40, and we know that fx is f cos theta, so it's 10 cos 40. So we get 6.4 newtons and 7.7 newtons respectively. So the two component forces added together give the same effect as the single force. Now remember, they don't have to add it directly to form the resultant, as you've also got to consider their direction. So let's look at another particular question. So for example, what are the horizontal and vertical components of a vector with a magnitude of 6 meters per second and a direction of 60 degrees from the horizontal? So we use our equations and we say, right, that x is going to equal cos 60 times by 6, so therefore it's going to be 3 meters per second to the right. We can then use our ideas of trigonometry to work out our answer of y, where y is equal to 6 times by sine 60, so you work that to 5.2 meters per second upwards. So therefore we've got now our resultant vector split into its two components. So the two component forces added together will give the same effect as the single force, but they don't add directly to form the resultant, as you've also got to consider their direction. Now we can also resolve vectors by using scale diagram methods as well. So you could look at the scale of your scale diagram, so say for example 1 centimeter equals 10 newtons. You then produce a right angled triangle with the resultant vector as the hypotenuse. So you've got your vertical vector, and you can work that out by measuring the length of the vertical vector with a ruler and convert it to a force via the scale. You would then measure the length of the horizontal vector with a ruler and convert it to a force via the scale. So just to clarify again, to resolve vectors by using scale diagram methods, you produce a right angled triangle with the resultant vector as the hypotenuse. You measure the length of the vertical vector with a ruler and convert it to a force via the scale. You then measure the length of the horizontal vector with a ruler and convert it to a force via the scale. Now remember, the two component forces added together give the same effect as the single force, but you don't have to add them directly to form the resultant, because you've also got to consider their direction. Now the question you've got to ask is, if we can split up a resultant vector into its horizontal and vertical components, why is this useful in the real world? So we could show this by carrying out an experiment such as dropping a ball off the roof of the school to measure how quickly it would take to hit the floor. So, if we carried out this experiment from a higher place other than the roof of the school, why would the experimental results be better? Well, the results would be better because the distance travelled is longer, so the time taken to fall is longer, so this means that the error of the time measurement has a smaller effect on the time measurement, so it lowers your percentage error in your measurement. Now, if we carried out the experiment from the roof of the school and there was a horizontal wind, would this affect the results of how quickly the ball fell, and why? Well, the results would not be affected because horizontal motion does not affect vertical motion. This is because when you resolve the forces into the horizontal and vertical components, they don't actually interfere with each other. So if we carried out the experiment from the roof of the school, what's the only factor that would affect the vertical acceleration? Well, the vertical acceleration is determined by the gravity of the Earth, because there's no resistive forces on the object and there's no additional push at the start. So the only force that causes acceleration is the gravity of the Earth. Now it's important to note that if we carried out the previous experiment from the roof of the school, what would determine the horizontal acceleration? Well, it would only be gravity, because gravity only acts in the vertical direction. There's no horizontal component of gravity, so that means there's no forces in the horizontal direction. So if there's no horizontal forces, there's no horizontal acceleration, so the horizontal velocity will remain constant. So this idea, it represents one of the most important principles in physics, the principles of projectiles. The idea that horizontal and vertical vectors such as forces or velocities are independent of each other. This means they do not affect each other. So this means that all objects fall at the same rate vertically, irrespective of their horizontal motion. This is because all objects experience the same vertical force, gravity. So this means a ball dropped sideways hits the ground at the same time as a ball dropped. This means that a parcel dropped from a moving car and a parcel dropped from a stationary car hit the ground at the same time. This means an object thrown from a moving train hits the ground at the same time as the object thrown by a person standing still. So because all objects are pulled to the ground via the force of gravity, all objects have the same downward acceleration. Any horizontal moving object experiences the same downward acceleration as other objects. So horizontal vectors do not affect vertical vectors. Vertical vectors do not affect horizontal vectors. So vectors at right angles to each other do not affect the size of each other. So vertical vectors will only affect vertical motion. Horizontal vectors will only affect horizontal motion. So only the vertical vectors acting on this object will affect its vertical motion, whether it accelerates in the vertical. The horizontal vectors would not affect this at all, and only the horizontal vectors acting on the object object would affect its horizontal motion, whether it accelerate horizontally. The vertical vectors would not affect this at all. This is why we've got to resolve a resultant vector into horizontal and vertical components to allow you to work out the horizontal and vertical motion on a component. So what have we learnt in today's lesson? That scalar quantities have a magnitude only. Vector quantities have a magnitude and an associated direction. A vector quantity may be represented by an arrow, and the length of the arrow represents the magnitude, and the direction of the arrow the direction of the vector quantity. The number of forces acting on an object may be replaced by a single force that has the same effect as all the original forces acting together, and this single force is called the resultant force. And you should be able to use vector diagrams to illustrate the resolution of forces, equilibrium situations, and the determination of the resultant of two forces. So if we've been successful and learnt in today's lesson, we should be able to define a vector quantity and how we can resolve them, describe how we represent vectors, and explain why we resolve vectors. So I hope you've enjoyed today's lesson looking at resolving vectors, which is part of the GCSE Separate Science topic of forces. Thank you very much for watching, and have a lovely day.